Thank you for the introduction. So yeah, this talk is about out-of-distribution generalization, and I'm a postdoc at UDM and Mila. And the work is a joint work with Ethan, Dingwai, John Christoph, Joshua, Ioannis, and Irina. And this work was recently accepted to NeurIPS 2021. And yeah, I'll start the presentation. So I'll start with the motivation. So say I'm asked to train a classifier to distinguish cows from camels, and typical images of cows have a green background, and typical images of camels have a brown background. So when the classifier is tested on images of cows, say on beaches with a blue background, the classifier fails. And that's quite problematic because like we want our machine learning systems to be actually using the shape of the cow, but not the background color to make the prediction, because background color has nothing to do with the cow. It's just a spurious correlation. So this type of problem, if it occurs in say self-driving cars or healthcare applications, it can be quite catastrophic. As an example, if I'm training my self-driving car models, like mostly in the day, and now when it is going to encounter traffic light during the night, that can be quite problematic. So these type of issues are addressed under the umbrella of out of distribution generalization. And now I will get into what is the core of the problem. So we're looking at the image of the cow. When a human is asked to generate the label, because the training data sets that we have are annotated by humans. So how does a human actually label the cow? The human sees the cow, ignores the background, just uses the shape of the cow to make the prediction that this is a cow. But when a machine learning model is used to make the prediction, it's actually seeing the background. Background is an easier thing to learn in this case. So it just uses that as a shortcut to make the prediction, because most of the times, whenever it sees a green background, it says, okay, it's most likely a cow. So the difference between green background and the shape is that shape is actually the cause of the label. Green background is just a mere correlation only present in my training data set. So what we would like is for our models to actually use truly the causes and to make predictions. By saying causes, I mean the things that are actually used to generate the labels. So these two things are fundamentally different. And this talk is about making our models or correcting our classical techniques in a way that they can actually use causes to do learning. So now I'll get into the problem formulation. Typically, in machine learning, we have data sets that are gathered from multiple environments. Say I'm given images of cows on beaches, cows in different areas. They're gathered in different locations. I would call them as training environments. And then I have to go and test my classifier in areas that were never in my training distribution. I call them as test environments. Formally speaking, I'm building a classifier F or a predictor F whose performance is going to be measured in some kind of a risk. You can think of the risk as the error the classifier sees. And my goal is to build a classifier, which I'm calling F, which is going to solve this formally stated objective, which is a min-max optimization problem, which stated in simple words is saying that I'm trying to solve for a worst case optimization, that no matter, like in the future, I'm going to see some environments that I don't know right now, which I'm writing as all the future environments that I can ever see. In those environments, my classifier should always work. So now the obvious challenge of this problem is that I cannot anticipate beforehand the kind of environments I'm going to see. So how do I build classifiers that can always work? So to think about such problems, the language of causality has tools to think about such problems, and we are going to leverage those tools. And to constrain ourselves to some settings, we are going to think in terms of data generation processes. So this figure that you see here, these two figures are trying to distinguish two types of common data generation processes that we see in reality. So here y's are shown as labels, z that you see here is written as latent variables, and x's are our observations. So x is to show that the pixels that you see in the image, z's are supposed to be divided into two parts, z inv and z spurious. The invariant part is the shape of the cow. The spurious part is the background of the cow. Y is the label that was generated. The two data generation processes differ by the fact that the spurious part, which is the background, in the left figure you see, does not carry any extra information about the label, all that is already contained in the foreground. But in the right figure that you see, the spurious factors have some extra information, but that information is not reliable. An example of that would be that if a human is given a blurry image of a cow with a green background, in such cases, human may use the green background to label the image, but that's not a really reliable feature. So you still would not really want to build classifiers that use backgrounds. So in such cases, there is formal theory which supports. There are works. I mean, including my past work, which shows that if you rely on causes, you can actually be OOD optimal. So if you can make your classifier focus on the causes, then you can solve the problem that I'd shown in the previous slide. That is the min-max optimization problem, provably. So now the key challenge, going back to the key challenge, is that we have understood what is the solution that we want to learn from causes. Now the idea is, how do we learn to predict from causes with a few environments or few training distributions? A very important work that led to many people thinking about these questions is invariant risk minimization. And invariant risk minimization is a paradigm which says, it's basically regularizes the classic empirical risk minimization with an additional constraint, which says that you will only search for predictors that are invariant predictors. And all of this mathematical formulation can be just in simple words stated as saying, I want to search for classifiers that minimize my total risk. That is the classical setting. But I also want to impose a constraint that if a classifier is optimal in one environment, it has to also be simultaneously optimal in another environment. So by imposing simultaneous optimality, they're in a way trying to constrain our search to predictors that would be close to the label generation process. So for such things, it was shown in these works that you can achieve a lot of success for linear regression tasks, that like even if you have a few training environments, invariant risk minimization paradigm showed a lot of success in theory, also in experiments for linear regressions that you can achieve or you can predict from causes. But what we found is when we implemented invariant risk minimization, and also what others found is when you implement invariant risk minimization in simple classification tasks, you still see failures. So what we went in this work is we dug a bit deeper into classification tasks to try and understand why these failures are happening. And we look at the data generation process, which is of the left kind in these works. So I will give an example of linear classification. So how much time do I have? 2 minutes left? Okay, so in linear classification, on this side, in this task, you're seeing there is invariant feature on the x-axis and spurious features on the y-axis. On the right, you have cows. On the left, you have camels. And in this slide, you can see there are 3 invariant predictors, but the one that is the sparsest one is the one that you actually want to learn from. The other 2 are not sparse, and those are the unreliable invariant predictors. But they can still be learned by invariant risk minimization. So how do we get rid of that? We say that if we impose an additional sparsity constraint, we can make our classifier focus only on the causes on top of invariant risk minimization. So our idea is to introduce an additional information bottleneck constraint, which will say that if you impose invariance and information bottleneck, you can restrict your classifier to focus on the causes only. I wouldn't have the time to go into some of these extra theory bits. So the main message is that if we basically restrict ourselves to these sparse invariant predictors, that is just take invariant risk minimization and impose additional sparsity constraints, that is the key to solving it. And that is formalized as this optimization objective, which says in the constraints, you are seeing invariant risk minimization constraints. And on top, you're seeing the information bottleneck objective. And we can show in theory also whatever this objective is proposed is actually solving the promise that in the cases where IRM and ERM fail, we achieve optimality or OOD optimality. We translate this objective and test it out in real data sets. which are proposed as challenge data sets. So I'm showing 4 of those data sets here. There are 4 columns in this slide you're seeing. The first column is empirical risk minimization. Second is information bottleneck empirical risk minimization. The third column is invariant risk minimization. And the fourth column is information bottleneck invariant risk minimization. So whenever you're adding this additional information bottleneck constraint, you will see that it's helping the performance a lot. And that's the key thing that we can see, that if as long as you can impose these constraints in a nice way, you can actually closely learn from causes in many cases. So that's all I wanted to talk about. And yeah, please, if you have any questions.